We have previously discussed the invention of the MRI machine, and in particular, how an MRI can be used to collect a T1 weighted anatomical image of the brain. Remember that a T1 weighted anatomical image of the brain looks like a wet specimen. That is, grey matter appears grey in colour and white matter appears white. The quality of these images has improved over the past 15 years or so, particularly with the advent of high field strength MRI scanners. Here are two images of the brain taken using a 3 Tesla MRI scanner and a more recent 7 Tesla MRI scanner. You can see the difference in the quality and in particular the differentiation between grey and white matter. Now, while the improvement in this image quality is certainly welcomed, it is the advent of image analysis techniques that use these T1 weighted images that has really given neuroscientists more tools to explore the human brain. One of the biggest advances in brain imaging analysis techniques over the past 15 years would be the invention of brain morphometry. Now, morphometry is the study of the size and shape of the brain and its structures, and is one of the most used modalities and analysis techniques in brain imaging. There are multiple techniques used to explore brain anatomy using these T1 weighted anatomical images. The two most common are grey matter volume calculations using a technique called voxel-based morphometry, and the second is the measurement of regional cortical thickness. Now, voxel-based morphometry is actually conceptually a rather simple technique. It's when an individual's brain image is warped to match a standard template. This process of warping to a standard template is known as spatial normalization. This process creates a deformation field, which is really a map of how far each voxel in the input image must move to land at the matching point in the template image. So in essence, if an area needs to be stretched to fit the template, it must have been smaller to start with, and vice versa. This spatially normalized T1 weighted anatomical image is then segmented into tissue classes, that is, a grey matter only image, a white matter only image, and an image containing the cerebrospinal fluid. Now, this segmentation is performed based on the intensity of the image as well as a probability map which indicates the likelihood of finding a given tissue class at a given location. In most studies, these images are then modulated by scaling the image intensities by the amount of contraction or expansion that has occurred during the spatial normalization process. This results in an image where each voxel's value represents its volume. Finally, the images are smooth, whereby the intensity of each voxel is replaced by the weighting average of the surrounding voxels. In essence, this blurs the segmented image. Now, the number of voxels averaged at each point is determined by the size of the smoothing kernel, which can vary across studies. Smoothing makes the data more normally distributed, increases the validity of parametric tests, and reduces inter-subject anatomical variability. Smoothing also increases the sensitivity to detect changes by reducing the variance across subjects, although excessive smoothing will diminish the ability to accurately localize changes in the brain, and will reduce the likelihood of detecting changes in small structures, for example within the brainstem. So just briefly, the original image is spatially normalized to a template, segmented into grey, white and CSF images. Now, in most studies, the grey matter image is then modulated to create images where each voxel represents volume, and finally, the grey matter volume images are then smoothed. We are now ready to perform statistical tests. So grey matter volume differences between, for example, a control population and a patient group can be determined in a relatively simple manner by comparing brain maps of grey matter between groups. So at each voxel, statistical differences between grey matter volume in the controls and the patients are compared. Given that you are effectively performing thousands of t-tests, the statistical threshold is then corrected for multiple comparisons. Furthermore, given the known effects of age, gender, and simply head size on regional brain volume, it is standard practice to factor these variables out during the statistical testing procedure. Probably the most famous example of voxel-based morphometry use was a very early study investigating the size of the hippocampus in London taxi drivers. Published in 1999, this study showed that the posterior hippocampus on both the left and the right side displayed greater volume in taxi drivers than in controls, and that the longer the time as a taxi driver, the larger the posterior hippocampus was. The authors state that this volumetric increase is quite consistent with the idea that the posterior hippocampus stores a spatial representation of the environment, and it can expand regionally to accommodate an elaboration of this representation in people with a high dependence on navigational skills. Now, this was a fascinating finding and opened a floodgate of studies using VBM to assess regional brain volume in all sorts of patient populations with various conditions. Overall, voxel-based morphometry is a relatively simple, automated analysis procedure that can provide a relatively crude indication of brain regions in which a change in local anatomy has occurred. What precisely reduction or increase in grey matter volume represents at a cellular level is open to interpretation. Increases could result from a range of changes such as dendritic sprouting, inflammation, glial activation, etc. What voxel-based morphometry does is give you a great starting point for further investigations, particularly in situations where there is very little prior information as to the neurobiology of a certain condition. Now, another variation on voxel-based morphometry type analyses is the use of a surface-based analysis, which essentially provides a measure of regional cortical thickness. Like voxel-based morphometry, surface-based analysis uses T1-weighted anatomical images to explore regional cortical thickness. The first process in surface-based analysis is to extract the cortex by defining the inner and outer margins of grey matter. This process is similar to that performed for voxel-based morphometry, in that the grey matter and white matter are defined in each individual subject. So one takes a standard T1 weighted anatomical image, removes the skull, and then defines the inner margin of grey matter, defined here by yellow, and the outer margin of grey matter, indicated by the red. The simplest procedure is to then draw vectors from the inside to the outside of the isolated grey matter and determine the length of each of these vectors. A map of the brain can then be created with each point in the brain color-coded for cortical thickness. As with voxel-based morphometry, each individual subject's brain image can be warped to fit a standard template so that each subject's brain is in exactly the same three-dimensional space. These maps can then be compared between groups, and areas that show significantly different cortical thickness measures determined between various groups of subjects or within a particular group of subjects. So just like voxel-based morphometry, a group of controls can be compared to a group of patients. And voxels in which there is a difference in cortical thickness can then be determined using multiple t-tests. Now, this procedure is sensitive to changes in regional cortical thickness, but unlike voxel-based morphometry, it cannot be used to explore changes in subcortical structures, such as the thalamus, basal ganglia, or the brainstem. A recent investigation explored the effects of smoking on cortical thickness. Remarkably, the authors found that cigarette smoking was associated with significant reductions in cortical thickness over almost the entire brain. Further, they found that this was dose dependent, with the greater number of cigarettes smoked each day associated with a greater reduction in cortical thickness. Remarkably, although the authors found that cortical thickness began to recover each year after an individual stopped smoking, it took on average 25 years for the brain's cortical thickness to return to control levels. Now, this is just one example of how one can use a standard anatomical brain image to explore regional brain anatomy. Although the two techniques outlined in this video are relatively crude in nature, they provide a great starting point, following which one can use other brain imaging techniques to obtain more specific information about the underlying cellular changes in various brain regions.